Hello, I'm Chen, a waste management engineer. I'm going to be presenting evaluations of on-farm centrifuge and screen on removing solids and nutrients from flush liquid dairy manure with two co-authors, Kevin Kruger and Howard Niblin. Kevin is here with me. He will also be presenting. All of us from the Department of Soil and Water Systems at the University of Idaho. For today's talk, we'll give you brief project background information, what we did, what we have found. So first, project background information. Idaho has a strong dairy industry and ranks among the top 5 milk producing states in the nation. As a byproduct of milk production, large amounts of manure are generated each year. Some ag dairies use liquid manure handling systems, either flushing their manure lands or mixing their equipment clean water with vacuum slurry manure from their manure land. That result in large amounts of liquid dairy manure. Solids and nutrients presented in liquid dairy manure pose challenges to manure handling processes. Most ag dairymen are familiar with the benefits of solid liquid separation and have installed primer screens that separate coarse particles from their liquid streams. A few dairies have incorporated secondary solid separation technologies, such as centrifuge and secondary screens, into their manure handling systems to realize higher solids and nutrient removing rates. Dairy producers have realized that separating solids and nutrients from liquid dairy manure is a critical step to realize better manure management. Ag dairymen want to learn more about solids and nutrient separation efficiencies by centrifuge and screens to make informed decisions on upgrading their solid liquid separation technologies. The objective of this study was to evaluate centrifuges and screens performance on removing solids and nutrients from liquid dairy manure and on affecting ammonia emission from their treated liquid dairy manure. What we did, we conducted year-long evaluations of on-farm centrifuge and screens on removing solids and nutrients and on affecting ammonia emission from flush dairy manure. Flush liquid dairy manure samples were collected monthly before and after screens and centrifuges from commercial dairy in southern Idaho. Meanwhile, screen and centrifuge separated solids were collected from the same dairy. The collected separate solids were analyzed for nitrogen, phosphorus, and potassium by a certified commercial laboratory. The collected liquid samples were analyzed for total suspended solids in our waste management laboratory at the University of Idaho Twin Falls Research and Extension Center. Ammonia emission from the monthly collected liquid dairy manure were also evaluated using ammonia passive samplers outside the waste management lab under seasonal conditions of the year. Ammonia emission rate was calculated based on the durations and ammonium nitrogen concentration from the agua ammonia passive sampler tests. Here is a liquid manure flow chart on the dairy. They have receiving pit where the barn milk powder clean water was mixed with a vacuum truck collects slurry manure. From there, pumped to a sand lens where some sand removed, then flowed to a pit, and went through two primer screen in parallel, and then to the two centrifuge again in parallel, and went through to their lagoons. From there, applied to the cropland and their irrigation systems. We collect liquid manure from the location we mark here, 135 That's before screen, after screen, and after centrifuge. Also solid from screens and centrifuge that's marked at 2 and 4. So Kevin will be talking about the ammonia test. So go ahead, Kevin, please.
Yep, thank you, Lita. The passive ammonia samplers were used to determine the time average concentrations of ammonia in the headspace of 5-gallon buckets containing the monthly collected liquid dairy manure. 4 replicates per treatment were tested by the passive samplers every month during the 1-year test period. The disassembled components of the passive samplers were thoroughly cleaned before placing them into the headspace of the buckets by rinsing with deionized water and soaking in 1 molar hydrochloric acid, rinsing again with deionized water, and then drying them in a clean hood. The passive sampler filters that you can see, that's number 3 in the figure, were prepared by saturating a clean filter with 100 microliters of 2% citric acid and air drying before assembling the samplers. Next slide. At ARS, researchers helped us to analyze these samples. 5 milliliters of 1 molar potassium chloride was pipetted into the centrifuge tubes with the filters. The solution was tested for ammonium concentrations using the QuickChem system. Next slide.
So we'll move on to what we found. So the picture shows a centrifuge and a screen separate solids. Left one centrifuge separated. We can see the screens only get the longer fiber out of the liquid stream, but centrifuge had a capacity to remove much finer particles. This is total nitrogen in the separate solids. The blue one is from screen separate solids. So this figure shows the total nitrogen concentration in the centrifuge separate solids higher than that in the screen separate solids. A year-long average of 9.2 pounds per ton of total nitrogen in the centrifuge separate solid compared with 5.4 pounds per ton in the screen separate solid. Here's the phosphorus in the separate solids. It's much higher concentration in the centrifuge separate solids compared with that in screen separate solids. A year-long average of 8 pounds per ton of phosphorus versus 2 pounds per ton in the screen separate solids. So they're almost 4 times higher in the centrifuge separate solids. Here's potassium concentration in the separate solids. Again, a centrifuge separate solids have higher potassium concentration, a year-long average of 7.2 pounds per ton of potassium compared with 4.4 pounds per ton in the screen separate solid.
Here we see total solids on the y-axis and time on the x-axis. The treatments before the screen, after the screen, and after the centrifuge were found to be significantly different for total solids. However, time was not found to be significantly different. Next slide. This has the suspended solids on the y-axis and time on the x-axis. The treatments before the screen, after the screen, and after the centrifuge were also found to be significantly different for suspended solids. However, time was not found to be significantly different. Next slide. Here we have ammonia emissions rate on the y-axis, and time on the x-axis. The treatments before the screen, after the screen, and after the centrifuge were found to be not significantly different for ammonia emission rate. However, time was found to be significantly different. Next slide. So here we have the ammonia emission rate as correlated to suspended solids. For each of the treatments, there was a negative slope relationship indicating that suspended solids decrease the ammonia emission as the ammonia emission rate increases. Next slide. Here we see the ammonia emission rate as correlated to temperature. For each of the treatments here, there was a positive slope relationship indicating that as temperature increases, the ammonia emission rate also increases. Next slide.
Okay, move on the take-home messages. From this test result, we can see centrifuge can further remove finer particles that cannot be removed by primary screens. Centrifuge separate solids contains higher nitrogen, phosphorus, and potassium, especially phosphorus. Again, average of 8 pounds per ton in the centrifuge separate solids compared with 2 pounds per ton of the phosphorus in the screen separate solids. Ammonia emission from raw liquid manure screen and centrifuge separate liquid manure did not show significant difference. The most influence factors for ammonia emissions from liquid manure were ambient temperatures and suspended solids content within the liquid air manure. So this study was supported by USDA NIFA via a Western SARA project. Also, many thanks to the scientists at USDA ARS Kimberly Research Station. So any questions or suggestions, please contact me at lchen@uidaho.edu or call me at 208-736-3615. Well, thank you very much for your time and attention.
Okay.